We are Team Greenbotics. I'm Rakshit.
I'm Devansh.
And I'm also Devansh.
This is our second year in the WRO FE.
Last year at WRO Internationals, our robot scored a full score in every round.
This is our new robot. We've redesigned every aspect of it.
We are going to explain what, why and how of every design aspect.
This is just the trailer. The full story is on GitHub.
Our chassis is rear wheel drive. We also moved to a metal differential. Plastic differential ground down and had backlash during parking. Metal is more efficient and precise. For steering, we upgraded from parallel to Ackerman. Parallel slip tires on tight turns, especially during parking. We calculated torque and speed before picking our motor. The old Lego motor was maxed out with zero headroom. We calculated ratios such as stall torque versus starting torque and running torque versus continuous torque to pick a theoretical best motor. The entire chassis is custom designed and 3D printed on Autodesk Fusion and was printed on the Bamboo Lab A1. Every part earned is placed through testing and not guessing. The battery splits the power into two rails, one for the Raspberry Pi with the sensors and the servo motor and the other for the drive motor. But now the question arises, this power architecture, can our battery handle it? Which battery is to be chosen? We measured real current draw against our power budget to confirm it holds up with tools such as multimeter and the telemetry. So we ended up choosing a 1500 mAh 3S LiPo. For sensors, we compared options for each job. TOF sensors, cameras and IMUs. We compared similar models and found out which was the best one for us. Placement mattered too. Our TOF sensors sit recessed since accuracy drops at the very edge. Every sensor has a documented calibration step before it's trusted on the track. Here's how we wired it together. This wiring can get messy. So we also created a custom PCB to mount all the components to get a clean and finished build.
We made HSV and gyro calibration tools to ensure our robot works well in all scenarios and lighting conditions. Every frame runs a priority state machine, avoid head-on, pass traffic sign, turn corner, wall follow, and parking. We start by converting the BGR frame to HSV, then perform a bilateral filter on it to reduce noise while keeping edges intact. We then apply a color mask and identify contours in it before annotating them on the frame. We specify ROIs for each color to reduce processing overload and only detect objects where needed. For obstacles, we steer using an angled target line, using a PD controller to ensure the actual line coincides with the target line. Our robot is a complex system where the battery powers all the components, sensors sense, and software thinks. The software then gives instructions to the mobility system to actually move the robot. These systems stay in sync in every frame and ensure the robot can move autonomously. Instead of relying on the external microcontroller, we harness the power of the onboard RP1 controller to generate jitter-free PWM signals and accurately count encoder pulses, all natively on the Pi. This single decision simplified our power, physical layout, circuit wiring, and software.
After assembly, our robot moved smoothly, but the camera feed was wobbly. We traced it back to a tiny misalignment in our 3D printed parts, which got amplified because the camera is mounted on a pillar. To fix it, we added a support bracket near the wheels and reduced the wobble. This is our GitHub repo. The entire robot design has been divided into 5 areas. We will directly go over the GitHub section so that we understand how to build the robot from scratch. This section goes over the structure of the repo, how to build the robot step by step, right from printing the 3D parts to fabricating the PCB to assembling it. Then you will see how we can set up the Raspberry Pi environment, clone the repo, and run the robot software. This is the schematic of our PCB. And these are the raw STL files for 3D printed parts. You could print them as is. These are isometric views of all custom components that we have printed. The source code is organized into functional sections. The open challenge, obstacle challenge, and the common code is in motors, sensors, and tools used for tuning and testing. This README will give you a brief walkthrough about software interfacing for each component. We use MATLAB to simulate the robot in a virtual environment. This allowed us to test and iterate faster.
Design.
Test, improve. This is Team Greenbotics.